Okay, we're on to 2.7, where we're looking at descriptive statistics still. Now we are looking at measures of the spread of data, or another way to say that is we're looking at measures of how variable the data is. And the ones that we're going to look at are just briefly range, and then variance and standard deviation. Standard deviation being the one that's most often used and talked about. All right, so to start off with range, it's kind of a quick and dirty way to look at the spread of data. It is the maximum value in the data set minus the minimum value. Now, you can see it only uses two values to calculate it, so it's only giving you an idea of the spread between the extreme values, so the smallest and the largest. Okay, the other two, variance and standard deviation, are both measures of the spread of the data within the extremes, and they are based on this idea of an average distance away from the mean, the sample mean or population mean, whatever the context is that we're talking about. That distance away or difference between the value, the data value, and the mean, we call that a deviation. Okay, so the standard deviation, all right, we can think of that as being the average deviation away from the mean. So I just want to kind of start off with that, because that word or that phrase can just have not a lot of meaning, but really what we're trying to get at is the average deviation or difference from the mean. In fact, let's just use that word. Okay, we're looking at what are all the deviations of the data values from the mean value. Okay, how much do they deviate? And we want to try to get at an average of those for this measure. We are going to derive the formula for standard deviation. It's just an average, and we know how to calculate an average, so we should be able to do that. So we have some sample data. There's the sample size is 5, and those data values are given there. What we're doing is we're looking at length of stay in the hospital for a sample of 5 car accident patients. So if we're looking for the average deviation, we are going to want to calculate what the deviation is between the data values and the sample mean. So to start off with, let's calculate X bar. Okay, so for X bar, we're going to want to add up those values of X and divide by the sample size of 5. All right, well, if we add up those values, all right, it's actually given to us. It's 25 divided by 5, we get sample mean of 5. Okay, now we want the deviation between each of those data values that are listed and that mean. So we want to really think about this difference here, X minus X bar. That is a deviation from the mean. And if we want to find an average, right, what we're going to want to do is add them up and divide. That's how you find an average. So let's go through and find that deviation for each of these values. So if we're going to take 3 minus 5, you get a negative 2, 4 minus 5, negative 1, 9 minus 5, positive 4, 7 minus 5, positive 2, 2 minus 5, we get a negative 3. Okay, so go ahead and add those up, and what do we get? Well, we get a 0. So that is really unhelpful, and it turns out that's exactly what should happen every single time if we have calculated the mean. If we take the straight deviations and we add those up, every single time they're going to be 0, and it just comes from how the average is calculated. Okay, so we're going to have to kind of figure out something else because the sum of those deviations is 0. Okay, what can we do to that x minus x bar so that when we add them up, they doesn't equal 0? Well, one thing we have going on here is these deviations, some of them are positive and some are negative. Turns out there's always going to be the right number of negative to cancel out the right number of positive. So we need to do something to that x minus x bar to make it all positive. So there's kind of two options, right? We can do absolute value or we can square. Turns out squaring is the better option. So we are going to take the sum of the xi's minus x bar squared. All right, so remembering our summation notation, we first are doing the subtraction, then we do the squaring, and then finally we do the adding up. So it's 1, 2, and 3. Okay, so let's go back up to our table and calculate these squared deviations. So what we're looking at is the x sub I minus x bar squared. Okay, well, we already have the xi minus x bar, so we just need to square that. So we're going to have a negative 2 squared. Now remember, when you square a negative, you're always going to get a positive. So you get 4 and then 1 and 16, 4, and a positive 9. Okay, now we have all positive numbers. When we add those up, we're going to get something positive, and that is 34 we get for the sum. Okay, so we have come up with this deviation from the mean. We've squared them, we've added them up, we've gotten this number 34. So it seems like to get then the average deviation, we would divide by the sample size, 5. Which seems like that is what we'd want to do. It actually turns out it's better to divide the sum of those square deviations by n minus 1. So in this case, it's going to be 4. Okay, so if we take the sum of those square deviations and we divide by n minus 1, that gives us the descriptive statistic sample variance. So we take the sum of the x, this is minus x bar squared, divide by n minus 1. That is what we get. That is sample variance. Okay, for the example, right, we found that numerator value, that's 34, and we're going to divide by n minus 1, or we're going to divide by 4. So that gives us a sample variance of 8.5. All right, yeah, we're rounding to 1 decimal place, which is what we end up with. Okay, so we have a formula for sample variance. We had to square those deviations, though, to get something that didn't add up to 0. So by squaring those, we now have this measure that has the original units or labels squared. So remember, our data values were days in the hospital. So instead of just having this variance that's measuring days, it's measuring days squared, which doesn't really make a whole lot of sense. Okay, so to undo squaring, then we're going to take the square root of that variance. And that gives us sample standard deviation. So we take the square root of all that, which we came up with for the variance. That gives us standard deviation. Okay, for our example, we had 8.5. So if we take the square root of 8.5, we're going to get standard deviation of well, it equals 2.91, and it keeps going, but if we want to round to 1 decimal place, that's just going to be 2.9. All right, now remember, since we've taken the square root, we're now back to the same units and labels as our data. So this is 2.9 days. Okay, so that's, if you remember, standard deviation is the average difference from the mean. So for those 5 patients, the average difference in the length of their stay from the mean of 5 days is 2.9 days. Okay, we've got the box here giving us the summary of how we calculate sample variance and sample standard deviation. That should say sample, sorry about that. And also we have some notation. For sample variance and standard deviation, we use S squared for variance. Okay, we got, see that right there? S squared stands for sample variance, and just S, all right, think of taking the square root of S squared, we get S, that is the sample standard deviation. So just a couple of reminders. N is sample size, X bar is the sample mean, and we're kind of adding to our list of sample statistics. S squared, and X bar are sample statistics. Now, what if we want to refer to population variance and standard deviation? Well, for variance, we use sigma instead of S. Okay, we had sigma for summation notation. When it is written like this is the lowercase sigma. Okay, so this was the uppercase, and what we use for variance and standard deviation is the lowercase. Okay, now the one thing that you'll notice is that for the variance we divide by n, we divide by the population size, okay, and instead of subtracting 1. Most of the time we're going to let technology calculate variance and standard deviation, but it's helpful to calculate it by hand a few times because I think it helps us understand actually what it is. So we have 2 small samples here. We want to find mean, median, range, variance, and standard deviation for both of those. So let's start off with the sample mean for this first one. We want to sum up those values. So -1, -3 is a -4, which is going to cancel out the 4. So the sum of those is 8. Divide by 4, so we get sample mean of 2. Okay, median. I'm just going to write the ranking of the data values next to it, next to them. The middle 2 values are -1 and 4, so for the median we're going to take the average. Adding those together we get a 3, divided by 2, so our median value is 1.5. Range. Take the maximum value of 8 and subtract the minimum value, which is a negative. So we got to remember, if we subtract a negative, that's like adding, so we get 8 plus 3, so our range is 11. Now let's look at variance. So start off, we're going to find the deviations and then square them. So -1 minus our mean of 2, that's going to be a -3 squared, so we get 9. -3 minus 2 will be -5. Squaring that, you get 25. 4 minus 2 squared, we're going to get 2 squared or 4. And then finally 8 minus 2 squared, we get 6 squared or 36. Okay, so adding those up, we get 73 for the sum of those squared deviations. So S squared, that's our sample variance. All right, we're going to take that, the sum of those squared deviations, 73, and divide by the sample size minus 1. So 73 over 3. You get 24 repeating 3. Now, usually what we're interested in is standard deviation. So if you have that in your calculator, you just want to go ahead and take the square root of it to get the standard deviation. instead of rounding and then plugging in the rounded value, you're going to get a more precise standard deviation if you just take the square root of the variance before it's rounded. Or, yeah, before it's rounded. Okay, so square root of 24 repeating 3, we get 4.93 dot dot dot, round to 1 decimal place, we're going to get standard deviation of 4.9. Okay, I would suggest pausing and working on the next one on your own, and then come back and check your work. All right, let's look at the mean of the second sample. So you want to add up those data values. So we get 2 plus 7 is 9, plus 11 is 20, plus 4 is 24. And dividing that by 4, we get sample mean of 6. And if we want the median, just order these values 1, 2, 3, 4. So the median is going to be the average of the 4 and the 7. So 11 over 2, so 5.5. Range. The max value of 11 minus the minimum value of 2, so we get a range of 9. Okay, now we want to get to work on variance and standard deviation. So 2 minus 6, square that. So we're going to end up with a negative 4 squared, so 16. 7 minus 6, which is a 1 squared, so that's a 1. 11 minus 6. Let me go back and fix that. There we go. All right, 11 minus 6 is 5 squared, we get 25. 4 minus 6, we get a minus 2 squared, we get a positive 4. So adding together those square deviations, we get 46. So sample variance, we take 46 divided by 1 less than the sample size, so divide that by 3. You get 15 point repeating 3. Now just take the square root of that for sample standard deviation. And 3.91 dot dot dot, so rounding to 1 decimal place, we get 3.9. Okay, so like I said, most of the time we can use a spreadsheet, we can use a graphing calculator or another app to find standard deviation. I have a link on Foxtail to an online tool that will calculate standard deviation for you. So if in an assignment you're just given data and you need to find standard deviation, feel free to use that. You may be wondering about using n-1 in the denominator of sample variance instead of just n. I kind of glossed over that. I didn't really give any reasons why. So I'm going to give you two answers. One short answer is if we just divide by n, it's going to underestimate the true population variance, or sigma squared. And by using n-1, it corrects that underestimation. Now, proving that is way beyond the scope of this course, something that is done in theoretical statistics. But we'll go through a longer answer that I think will help to understand why we want to multiply by n-1, which we just want to, n-1 is always going to be something less than n. Okay, so why we want to multiply by a smaller quantity than n. All right, so long answer is that population values are more spread out than any sample values. So if we think of, say, our population values, maybe go from a minimum value, I'm going to just call that population min, We could even say, let's just say it's 0, up to whatever the possible maximum value is, and let's just say it's 100. Okay, this is all the possible values that we could sample from. Now, if we think about taking a sample, like let's just say these blue marks are values that we get between 0 and 100 for our sample. Okay, well, it's unlikely that we're going to happen to pick the 0, the minimum value from the population, and the maximum. So you can see that the sample values are less spread out than the population values. All right, the difference between the population max and population mean is going to be greater, a bigger number than the difference between the sample max and the sample min. All right, so that also means that the sample values are going to be closer to the sample mean than population values are to mu. Okay, if sample values are less spread out, they're going to be closer to the mean value than population values are to the population mean. Okay, so just kind of following along with that, that means that when we take the differences between population values and population mean, add them up and square them, that is going to be a larger value. Those values x are further away, so they're going to have bigger differences, and then you square them and you add them up. It's going to be bigger than when you take the sample value, which are closer to the sample mean, find those differences, square them, and add them up. Okay, so we get the numerator part of our variance for the population is larger than for the sample. Okay, so if we divide just by n, okay, we take something that's larger than the other, we divide them both by the same things, well, they're going to have the same relationship again. Okay, so if we divide both of these by n, we're still going to have that same, that the population side is going to be greater than the sample side. So to compensate, all right, we divide that numerator by a smaller number. And when you divide by a smaller number, it makes the entire fraction larger. And so if it's larger, it's more likely to estimate the true population variance. Now we're going to look at an application of standard deviation, which is z-scores. Z-scores are going to help us compare across different populations. So let's look at this exercise from the textbook. An elementary school, middle school class, high school class ran 1 mile, and the mean and standard deviation are in the table. So using that information, we can answer this first question: which school level has the least variability in time? Okay, well, remember, standard deviation measures variability. So smaller the standard deviation, the less the variability. So the smallest standard deviation we have is for the middle school. So the middle school class had the least variation in their mile times. What about the most variability? All right, well, it's going to be the largest standard deviation, which is a high school. Okay, so the next thing we want to do is compare the mile times of the 3 students listed below with respect to their class. Okay, Rachel ran the mile in 8 minutes, elementary school. The middle school student, Kenji, she ran the mile in 8.5 minutes, 8.5 minutes. And Netta, a high school student, ran the mile in 8 minutes. Okay, just from those 3 numbers, we're not going to be able to answer those questions because they each relate to a different group and with a different mean and different standard deviation. So we want to use something called a z-score that will allow us to compare values from different populations. So z-score is the number of standard deviations away a value is from the mean. So a z-score is the number of standard deviations. And here's how we calculate. So if we have a sample, all right, we calculate z equal to whatever the value is minus the sample mean and divided by the sample standard deviation. And then we have a comparable z-score calculation for population where we just replace the x bar with mu and replace the s with sigma. Okay, so key things to remember. X is just a value from the sample or the population. The other thing is we always round a z-score to 2 decimal places every single time. So let's start off by finding the z-scores for the 3 students' mile times. Okay, Rachel is the elementary school student. So here I'm just going to rewrite the appropriate formula. Okay, so remember the x is the data value that we are finding the z-score for, and so the data value is her mile time, right, which is 8. And then we subtract the mean mile time for her class, which was 11, and then that difference we're going to divide by the standard deviation of 3. Okay, all right. 8 minus 11, we get a negative 3. Divide that by 3. And z-score is a negative 1. So Rachel ran her mile time 1 standard deviation faster than the mean of the class. So her mile time was 1 standard deviation below the mean. All right, that negative says that it's less than or below the mean. All right, let's see, what about Kenja? Kenja's mile time was 8.5, 8.5 minutes. And the middle school mean was 9. And the middle school standard deviation is 2. So doing the subtraction in the numerator, we get a negative 0.5. Divide that by 2. We get negative 0.25. Negative 0.25. All right, so Kenja also ran below the mean, so she ran faster than the mean mile time in her class. But it's closer to the mean. It's not, it's closer to 0 than the negative 1. So she wasn't as fast relative to her class as Rachel was to her class. So let's check out Netta. So Netta's time was also 8 minutes. That is relative to the high school mean, which was 7, and then divide that by 4, standard deviation. So we get 1 over 4, or positive 0.25. So Netta's time, he ran a time that was 0.25 standard deviations above the mean, all right? Or in this case, since we're talking about time, it was slower than the mean. So who ran the fastest with respect to his or her class? All right, well, we already kind of talked about this. So we basically want the one that got the time that is with the z-score that is the most negative. Okay, so that's Rachel. All right, Rachel's time is below the mean, so faster than the mean time. All right, and then the slowest is, well, the only one that has a positive z-score, which is Netta. All right, his time is above the mean. Okay, All right, so if we find z-scores, then we just can compare those across different populations to determine, to compare relative to their own population. Okay, so let's look at another thing that we can do with z-scores. What is the mile time for a middle school runner that corresponds to a z-score of 0.5? Okay, so what we're asking for is a mile time, and remember, that's what X is standing for. Those data values were mile times, so we're looking for X, and our formula includes an X, includes a Z. So now instead of taking a value and plugging it in for X, what we're given is the Z. So we'll just replace Z with 0.5, and what we don't know is X. And we do know X bar for middle school is 9. And standard deviation is 2. Okay, so it's just a little bit of algebra. Multiply both sides by 2. So we get 1 equals X minus 9. Add 9 to both sides, so we get X is equal to 10. And what we're being asked for is mile time. So you can say X is equal to 10 minutes, has a z-score of 0.5. Okay, another one of those. This time we're looking for the mile time that corresponds to a z-score of negative 0.75. So again, we're just basically plugging in the stuff that we know. So what we know is z is equal to negative 0.75. What we're looking for is x. We know that the mean is 9 and standard deviation is 2. So multiply both sides by 2. So we're going to get a negative 1.5 equal to x plus 9. Actually, that should be minus 9. Add 9 to both sides. So we get x equals 7.5. And it's a mile time, so we can label it with minutes. Okay. Okay, so we're going to look at z-scores pretty frequently throughout the course of the term. And so we're really just wanting to get familiar with them in this section. One of the takeaways is a positive z-score indicates that the value that it corresponds to is above or greater than the mean. And if it's negative, indicates that the value is less than the mean. All right, so here's a question. What about if a z-score of 0 What does that mean? Well, the only way that it can be 0 is if x is equal to the mean. All right, so the mean value has a z-score of 0 because it is 0 standard deviations away from the mean. Okay, we have another application of z-scores that we want to look at, and we're going to revisit this idea of outliers. And we can test for outliers using the quartiles like we did before, and sometimes that's the appropriate method, and sometimes if we have mean and standard deviation calculated already, we can actually use those to determine whether we have outliers. So remember, an outlier is a value in a data set that's unusually large or small relative to the other values. So let's look at this example. The sample number of goals scored by a soccer team in a game. And so it lists it out there in our question, is 14 an outlier? So The approach we use with a z-score is called the rare event approach. And it says that data values with z-scores greater than 2 in absolute value are considered possible outliers. So greater than 2 or less than -2. So let's test 14 in the example. So okay, so just a reminder, we're going to take z equal to x minus x bar divided by s. So our value is 14. The sample mean is given to us there as 3.6. Sample standard deviation is 4.2. And that gives us a z-score of 2.476 ... Round that to 2 decimal places, we get 2.48. Okay, well that is over 2. So we can say that, yes, 14 is an outlier. Okay, so we're going to revisit the reasons why we might have an outlier and think about those in the context of this particular problem. Okay, just identifying that we have an outlier doesn't mean that we throw it out, doesn't mean that there's anything wrong with it, but we do want to consider where it might have come from. Okay, so given that this 14 is in this data set, and we've said that it's an outlier, we want to consider if possibly the value is observed or recorded incorrectly. And that's possible. It could be that, you know, it should be 4 instead of 14. Like someone, you know, data entry, they accidentally did a 1-4 instead of a 4. All right, so we either need to fix it or throw it out. If we can fix it, we want to fix it, or we should throw it out. Or the value could maybe come from a different population. Maybe the 14 is a football score instead of a soccer score. That would make a lot of sense for it to be a football score. So if we can identify that it was supposed to be a football game score, then we are just going to take it out because it's not appropriate. It's not the same population. All right, and then the last possibility is the value is correct. We can't rule it out because of error or that it's from a different population. The value is correct. It just represents a really rare event. Maybe the team they were playing against was down some players and really having a bad day, and this team that got 14 was having a really great day. Okay, so that would make that possible. Okay, that wraps up 2.7.